The obvious diagnosis when latency starts climbing? You need more hardware, more GPUs, more memory, more throughput. But zoom into what the GPU is actually doing. And the problem isn't capacity, it's redundancy. Most of the work the GPU does has already been done before. Repeated key computations, repeated value computations. The same work, running again and again. This cluster doesn't need more power. It needs a memory of what it already computed. Why? Zoom into a single request. Token 1 arrives. The model runs a computation and produces a key vector and a value vector. One block of work. Token 2 arrives. It needs to attend to token 1, so the model recomputes token 1's key value pair, plus its own. That's 2 computations for 2 tokens, and one of them is a duplicate. Token 3 recomputes 1 and 2, plus itself. Token 4 recomputes all 3 before it. Token 5, all 4. See the pattern? The waste doesn't grow linearly. It grows as a triangle. Every new token recomputes every token that came before it. The longer the sequence, the more of the GPU's time is spent on work it's already done. But look at token 5's KV state at step 6, step 10, and step 15. Same state, every single time. Why? Because that state depends on the token, its position, and the prefix before it, not on the tokens that come after it. Once token 5 has been processed, its key and value are fixed. So compute them once and store them. When token 2 arrives, it doesn't recompute token 1. It fetches the cached result. Token 2 computes only its own vectors and stores those too. That's the KV cache. Token 3 reuses 2 cached pairs, computes 1 new. Token 4 reuses 3, computes 1. Every token pays for itself and nothing more. The staircase from before? It collapses to a flat line. Quadratic to linear. Redundant computations? All gone. Or are they? 1 request, solved. Now zoom out. 10 requests arrive in the same second. Every single one starts with the same system prompt. 200 tokens. Identical. Each request builds its own KV cache. From scratch. 10 independent caches. Each one storing the exact same key value pairs for the same 200 tokens. Scale that to 1,000, and the system prompt is computed 1,000 times. 999 of them redundant. We solved redundancy within a request. But across requests, there's an entire layer of redundancy we haven't touched. The missing piece is sharing the cache across requests. RadixAttention does that with a shared KV cache, organized as a tree. Here's how it works. First request arrives, computes the system prompt. Those KV states populate the tree's root path. Second request, same system prompt. It moves fast through the cached tree. Every KV vector already there. It branches only where its unique tokens begin. 200 tokens of computation, skipped. Third request shares the system prompt, plus a RAG context chunk. It walks the cached prefix, then extends the tree with the new context. Fourth request, same structure, walks the entire shared path for free. The tree grows richer with every request that passes through it. Each new request only pays for its unique suffix. Shared prefixes, however long, are computed once, stored once, reused every time the path matches. So what does the tree actually buy us? At 10 requests, most prefix work is shared. Get to 100, the cache is rich. New arrivals almost always find a cached path waiting. You serve 1,000 concurrent requests, and your system prompt was just computed once. You have a shared RAG context. Everything else is the only new work. And the savings aren't additive, they compound. More requests sharing structure means each new request pays less. Same GPU, same model, faster outputs. The only difference is what the system remembers.